at least some order, partial orders and lattices. The notion of partially ordered sets. Let us assume that you are looking for air tickets for your upcoming trip. There are 5 different airlines offering service to your destination, and you know what each of them would charge for a ticket. However, price is not the only important criterion for you. The duration of the flights also matters a little bit. In other words, if airline X offers a lower price and a shorter flight time than airline Y, then you say that the offer of airline X is a better offer. Assume the offers from the 5 airlines are as follows: A. $600, 9 hours and 20 minutes. B. $650, 8 hours and 40 minutes. C. $550, 9 hours and 10 minutes. D. $575, 8 hours and 20 minutes. E. $660, 9 hours and 5 minutes. For example, the offer of airline D is clearly better than that of airline E, but there is no such clear-cut difference between the offers of airlines C and D. You can represent the entire complex situation with the diagram shown in figure 16.1. In this diagram, the dots correspond to the offers. If an offer X is better than another offer Y, then X is above Y in the diagram, and there is a path from X to Y so that when we walk through that path, we never walk up. This was an example of a partially ordered set, the main topic of this chapter. The reader probably sees the explanation for this name. Some, but not entirely all, pairs of our elements were comparable. The time has come for a formal definition. Definition 16.1. Let B be a set and let less than be a relation on P so that A less than or equals to. Let less than or equals to be a relation on P so that A less than or equals to is reflexive. That is, X is less than or equals to X for all X in P. B less than or equals to is transitive. That is, if X is less than or equals to Y and Y is less than or equals to Z, then X is less than or equals to Z. C less than or equals to is antisymmetric. That is, if X is less than or equals to Y and Y is less than or equals to X, then X is equals to Y. Then we say that P less than is equals to the tuple P and less than or equals to is a partially ordered set or poset. We also say that less than or equals to is a partial ordering of P. Just as for the traditional ordering of real numbers, we write x less than y if x is less than or equals to y, but x is not equals to y. When there is no danger of confusion as to what the partial ordering less than or equals to of P is, we can write P for the poset P less than or equals to. If for 2 elements x and y of P, neither x which is less than or equals to y nor y which is less than or equals to x holds, then we say that x and y are incomparable. Example 16.2. Let P be the set of all subsets of n braces, and let A less than or equals to B if A is a subset or equals to B. Then P less than or equals to is a partially ordered set. This partially ordered set is denoted by Bn and is often called a Boolean algebra of degree n. Example 16.3. The set of all subspaces of a vector space ordered by containment is a partially ordered set. Example 16.4. Let P be the set of all positive integers and let x which is less than or equals to y. If x is a divisor of y, then P less than or equals to is a partially ordered set. Example 16.5. Let P equals to R, the set of real numbers, and let less than or equals to be the traditional ordering. Then P less than or equals to is a partial order in which there are no 2 incomparable elements. Therefore, we also call R a total order or chain. Example 16.6. Let P be the set of all partitions of n braces. Let alpha and beta be 2 elements of P. Define alpha which is less than or equals to beta if each block of beta can be obtained as the union of some blocks of alpha. For instance, if n is equal to 6, then the collections of the set 1, 4, 2, 3, 5, and 6 is less than or equals to the collection of sets 1, 4, 6, and 2, 3, 5. Then p less than or equals to is a partial order, which is often called the refinement order and is denoted by pi n. If x is in P is such that there is only y in P for which x is less than y, then we say that x is a maximal element of P. If for all z in P, z is less than or equals to x holds, then we say that x is the maximum element of P. Minimum and minimal elements are defined accordingly. The reader should verify that all finite posets have minimal and maximal elements. Not all finite posets have minimum or maximum elements, however. The poset shown in figure 60.1 does not have either. The minimum element of a poset, if it exists, is often denoted by 0 hat, while its maximum element, if it exists, is often denoted by 1 hat. If x is less than y in a poset P, but there is no element z in P so that x is less than z less than y, then we say that y covers x. This notion enables us to formally define Hasse diagrams, the kind of diagrams we informally used in our introductory example. The Hasse diagram of a finite poset P is a graph whose vertices represent the elements of the poset. If x is less than y in P, then the vertex corresponding to y is above that corresponding to x. If in addition y covers x, then there is an edge between x and y. Note that the condition that the vertex corresponding to y is above that corresponding to x makes it unnecessary to direct the edges of the Hasse diagram. Example 16.7. The Hasse diagram of B3 is shown in figure 16.2. Hasse diagrams are useful to visualize various properties of posets. In particular, they can help us decide whether two small posets are isomorphic or not. We can hear the complaints of the reader that we have not even given the definition of isomorphism of posets yet. This is true, but the definition is the obvious one. That is, two posets P and Q are called isomorphic if there is a bijection F which maps from P to Q so that for any two elements x and y of P, the relation x less than or equals to Py holds if and only if f of x less than or equals to Q f of y. It is easy to verify that up to isomorphism, there is one element poset, two element posets, and five three-element posets. The Hasse diagrams of the latter are shown in figure 16.3. The reader is invited to find all 16 four-element posets. We have defined chains in example 16.5. To see a finite example, in B4, the set of subsets 2, 3, 3, and 1 to 3 is a chain, as we have the set 3, which is less than or equals to the set 2, 3, which is less than or equals to the set 1, 2, 3, 4. The dual notion is that of anti-chains. If the subset S, which is subset equals to P, contains no two comparable elements, then we say that S is an anti-chain. For example, the collections of sets 2, 3, 1, 3, 3, 4, and 2, 4 forms an anti-chain in B4 as none of these four sets contains another one. It is straightforward that any subset of a chain is a chain, and any subset of an anti-chain is an anti-chain. A chain cover of a poset is a collection of disjoint chains whose union is the poset itself. It seems plausible that if a poset has a large anti-chain, then it cannot be covered with just a few chains, and vice versa. The following classic theorem shows the precise connection between the sizes of anti-chains and the chain covers of a poset. Just as for matchings, a chain, respectively anti-chain, X of P is called a maximum if P has no larger chain, respectively anti-chain, than X, and X is called a maximal if it cannot be extended. That is, no element can be added to X without destroying the chain, respectively anti-chain property of X. Theorem 16.8, Dilworth's theorem. In a finite partially ordered set P, the size of any largest anti-chain is equal to the number of chains in any smallest chain cover. Prove let A be the size of a largest anti-chain A of P, and let B be the size of any smallest chain cover of P. Then it is clear that A is less than or equals to B. Indeed, no chain can contain more than one element of A, so at least A chains are needed in any chain cover. We will have to prove the converse, that is, if the largest anti-chain of P is of size K, then P can be decomposed into the union of K chains. We prove this by induction on N, the number of elements in P. The initial case of N equals to 1 is trivial. Now let us assume that the statement is true for all positive integers less than N. We distinguish two cases. First, let us assume that P has a k-element anti-chain A that contains at least one element that is not minimal, and has at least one element that is not maximal. Then A cuts P into two, that is, into the sets U and L, where U is the set of elements that are greater than or equals to the at least one element in A, and L is the set of elements that are smaller than or equal to at least one element in A. Note that U intersect L is equal to A. As A contains non-minimal and non-maximal elements, U and L are non-empty, and they both are partially ordered subsets, with the ordering of P naturally restricted to them. Moreover, they have less than n elements, so the induction hypothesis implies that they are both unions of K chains. Each of the K chains in U has one of the K elements of A at its bottom, and each of the K chains in L has one of the K elements of A at its top. Therefore, these two K chains can be united to K chains covering P. Now let us assume that P does not have an anti-chain like the anti-chain A of the previous case. That is, all maximum anti-chains of P consist of maximal elements only, or minimal elements only. That necessarily implies that they contain all minimal elements or all maximal elements. Let X be a minimal element of P, and let Y be a maximal element of P, such that X which is less than or equals to Y. Let P' be the poset obtained from P by omitting X and Y. Then the largest anti-chain of P' has k-1 elements, as it cannot contain all minimal elements or all maximal elements of P. Moreover, P' has less than n elements, so by the induction hypothesis, it can be decomposed into k-1 chains. Adding the two-element chain X less than or equals to Y to this chain cover of P', we get a k-element chain cover of P. So if P is an n-element poset, then a linear extension of P is just an order-preserving bijection from P onto n braces. That is, if X is less than or equals to Y in P, then f of X is less than or equals to f of Y in n braces. Example 16.9. The poset shown on the left in figure 16.4 has two linear extensions, f and g, where f of a is equals to g of a equals to 4. F of d is equals to g of d equals to 1. F of b is equals to g of c is equals to 2, and f of c equals to g of b is equals to 3. The poset shown on the right in figure 16.4 has four linear extensions, as EF, the set EF can be mapped onto 3, 4 in two ways, and GH can be mapped onto 1, 2 in two ways.